All right, so we looked at work done when the forces acting on a system are, or on an object, are conservative. And so now we're going to look at work done on a system when some of the forces might be non-conservative, such as friction. Friction is a non-conservative force. You cannot get that energy back from friction. So what we say is perhaps there's an increase in thermal energy. For instance, you slide a sandpaper against a piece of wood, it's going to heat up. Okay, so because of the friction, there can be heat transfer due to sliding. And so what we can say is we're going to say that the change in thermal energy is due to friction. Now, when we work this out, we're going to do an example that doesn't necessarily need this formula first. But when we first work this out, usually work done by a conservative force only depends upon the displacement of the object. It's not path dependent, but friction is path dependent. Okay, it does matter how you travel from point A to point B because it's how long the object was in contact with the surface is going to depend upon how much, or is going to be a predictor of how much energy was lost because of that sliding. Okay, so let's do this quick problem. A food shipper pushes a wood crate of cabbage heads, I don't know why there's cabbage heads, with a combined mass of 14 kilograms across a concrete floor with a constant horizontal force of magnitude 40 newtons. In a straight line displacement of half a meter, the speed of the crate decreases from 0.6 meters per second to 0.2 meters per second. So let's write down what we know really quick. We start out at 6 meters per second. We end up at 0.2 meters per second. So that means that our change in kinetic energy should be negative because we're losing energy in the system. Okay, that's unfortunate for us. It's slowing down, so we're losing energy. Okay? But that's strange because we know that we're adding energy to the system with the supplied force. It's positive. Okay, so that means that something else is taking energy away. So the work done by the applied force should be equal to the applied force times the distance of that. So let me move down here. And that should simply be 40 times a half, and this would be in joules. So what does that mean? That means the applied force adds 20 joules to the system. But why does it slow down? Well, that means that perhaps there is an increase in thermal energy. Okay, that means that perhaps friction or something, drag, or anything else is taking energy from the system, and it's just not enough to compensate for the 20 joules. Okay, so let's look at the increase in this energy. So the net work done, the way to look at that means it should be equal to the change in kinetic energy. Okay, so the net work should be the applied force in the positive direction minus, we're going to call this the work done by, or the work done by friction or drag, that's an F, or anything else. Okay, and that should equal the change in kinetic energy, which is 1/2 the mass times the difference in the square. We know the work applied is 20 joules. Okay, perhaps I should leave off the units. Just add the units back in. We're going to find this energy lost due to, because it was changed to thermal energy or something. We can call it work or energy, it doesn't matter, same thing. Okay. The mass is 14 kilograms. The final speed was 0.2 meters per second, and the initial speed was 0.6 meters per second, because remember, it's slow. Now, this ends up being negative 2.24. Okay, and then we're going to subtract the 20. And this tells us that the negative thermal energy is equal to the negative 22.24 joules. Okay, so the negative just means, you know, if we divide by the negative, we'll get the magnitude. Okay, so the overall energy loss due to friction, drag, whatever, is 22.4 joules lost. Okay, they were converted to something else in the system, which is why it slowed down. We're only adding 20 joules to the system, but we're taking 22 joules out, so it had to slow down. Great. We look at this as we've done it before. where we look at the total energy of the system should be equal at any given time. That's true, but now we have an external force, something extra. Okay, this external force is getting in our way. And so how we're going to look at this external force is, yes, if these were conservative forces, this first part should be true. We're saying this is our initial, but then what this is should be what it would be if it was conservative. However, we've lost some of that friction ideally. And this last component, the energy from the thermal that's been converted to thermal, just needs to be added back in. This is just what I like to think of it as compensatory energy, just it's the sum of everything else. And if it is due to friction, then we can use the force of friction times the distance in which the object was interacting with that surface. So we're going to do one problem together. The figure shows a water slide in which a glider is shot by a spring along a water-drenched, frictionless track. Okay, so this part here is frictionless. No friction, thanks to the awesome water and all that. And it's gliding, then it glides into this horizontal section down here at ground level. It is gradually brought to rest by friction here, okay? So there's probably a lot of drag as well in here, but remember, drag acts just like friction. So as the glider then moves along the ground level track, it is gradually brought to rest by friction. The total mass of the glider and its rider is 200 kilograms. Let's write that down. The initial compression of the spring is 0.5 meters. So we can look at this as our change in x. It's 5 meters. The spring constant, oh, that should be an exponent there, is 3.20 times 10 cubed newtons per meter. So basically 3,200 newtons per meter. The initial height is 35 meters. That's where we're starting from. And the coefficient of friction along the ground level track is 0.8 meters. So mu k here is 0.8. Okay. Through what distance L does the glider slide along the ground level track? So this is what we're looking for. What is L? What is the distance that the rider travels before it comes to a complete stop? Well, let's see. All right, so let's set this up as we've done before. Okay, we have initial energy, potential, and initial kinetics should equal anywhere else in the system. Final potential energy, final kinetic energy. And in this case, we're saying that it's slowing down here. So there has to be energy lost because of the friction. It could be transferred to heat or drag or whatever. Okay, remember we're saying this is our initial and this is our final here. Okay, so let's think about initially. It should be energy from the spring and energy to gravity. So remember, this is going to be H equals 0. That just makes sense to have an initial position or initial placement of 0 in the y direction right here at ground level. So we're going to have, oops, jumping ahead, we're going to have gravitational potential energy and potential energy stored in the spring as well. But it's not moving when we first start. Okay. Now, finally, if this is the final part right here, we don't have any stored energy anymore. In fact, we're saying it's not moving anymore either, so there should be no kinetic energy. And so if we think about that, that means that all the energy is stored here. It moves around, blah, 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 turns into kinetic, and then once it gets here, all of that energy now dissipates thanks to the thermal, thanks to being converted to thermal energy because of friction. Thanks, friction. Okay. All right, so this should be mgh. This is 1/2 kx squared because it's a spring. And then if it's friction, remember work is force times displacement, and in this case it's the force times the distance it travels. Okay? We're going to change distance to L to use the variable that we're given here. Alright, so we have all these values. Let's first calculate friction. Alright, so here's your dude in a boat. He's very happy to be in his boat. There's some water. We're going to assume that he's floating. So if your normal force and your gravitational forces should be equal to one another. But now we have friction acting in the opposite direction. It's causing you to slow down. So what we have to remember is the force due to friction is equal to the coefficient of friction times the normal force. Okay, and in this case, we know the normal force must all over the place. So these both must be equal to mass times gravity. So we'll have mgh plus 1/2 kx squared is equal to mu k mg times L. Remember, we're trying to solve for L, so divide everything by mu k mg. And plugging in all those values, which you can take a moment to do that, this should equal 69.239 meters about. All right, so for tomorrow, I just want you to answer these 14 questions. They are simply true or false. True, if obviously these statements about work are true, and false if they're false, obviously. And we will discuss these tomorrow in class, and then we're going to work on a bunch of practice problems and begin reviewing for your EQT. Okay, see you tomorrow.